Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello everyone and welcome to this lecture in the Build DeepSeek from Scratch series. Today we continue our journey in understanding mixture of experts. Our main aim today is to learn about two things which are implemented in the mixture of experts modeling to make sure that every token is routed to experts in a balanced manner and all the experts are essentially utilized. One such method is called as auxiliary loss, and the second method is called as load balancing. Today we are going to learn about both of these methods, which are very commonly implemented in mixture of experts. First, let me quickly recap what all we have seen so far. In the first lecture on mixture of experts, we understood the introduction regarding how mixture of experts is essentially used in this feed forward neural network of the transformer block. And we also understood the intuition behind mixture of experts, this whole idea of sparsity. So every token is not routed to all of the experts, but only a select set of experts. And in the previous lecture, we saw a hands-on demonstration of how mixture of experts is actually implemented from scratch. We saw something which is called as top K load balancing, which means that every token is routed to only a select set of top K experts to implement sparsity. And the second concept which we saw is that of the routing mechanism. So the main idea of the routing mechanism is that the input matrix is essentially multiplied by the routing matrix, and we get something which is called as the expert selector weight matrix. And this expert selector matrix helps us to do two things. It helps us to understand which among the three experts in this case to route to every token or to route for every token. And the second thing it helps us understand is how much weightage we need to give to each expert whenever a token is routed to it. We learned about these steps in the previous lecture. So if you are unsure about this, please go back and revise the previous two lectures on mixture of experts. Today we are going to directly start from step number 8 over here, which is called as auxiliary loss. Now what exactly is auxiliary loss and why do we need it? So let us start understanding regarding this. In mixture of experts models, the routing mechanism essentially selects a subset of experts. As we have seen, for every token, we select a subset of experts which the token is routed towards. Until now, whatever we have seen so far, we have not implemented a mechanism which makes sure that this routing is balanced. which means that sometimes what can happen is if some experts get chosen or selected a lot of times while other experts are not utilized at all, it leads to inefficient learning and our performance is not as optimal as expected. Ideally, we want all of our experts to be helping, we want all of our experts to be contributing. So if we look at the entire data set and if we look at all the experts, I want all of my experts to be active somewhere. I don't want some experts to be overutilized and I don't want some experts to be underutilized. So to make sure that imbalanced expert selection is not there, we add a term which is called as the auxiliary loss term. So when the LLM is trained, all of us know that the main task of a large language model is the next token prediction, and we have the training loss at that time. Now, to make sure that the selection of experts is balanced, an auxiliary loss term is added to the main training loss term. And this penalizes imbalanced expert selection and it pushes the routing function towards a more uniform distribution. Towards a more uniform distribution of what? Towards a more uniform distribution of where the tokens are routed to. So let's say at the end of all the routing, you look at all the experts. Ideally, you want to see every expert processing similar number of tokens. Ideally, that's the balanced distribution. So now let me illustrate step by step to all of you how the auxiliary loss is actually calculated. So to start understanding how the auxiliary loss is actually calculated, we start looking at the expert selector weight matrix. And to give you a recap of what this expert selector weight matrix means, every row illustrates the experts which are assigned to that particular token. So if you look at row number 1, what it tells me is that token number 1 will be routed only towards experts number 2 and experts number 3, and a weightage of 0.6 needs to be assigned to expert 2 and a weightage of 0.4 needs to be assigned to expert 3. Similarly, token number 2 needs to be routed towards expert 1 and expert 3, and a weightage of 0.9 will be assigned to expert 1 and a weightage of 0.1 will be assigned to expert 3. Token number 3 will be routed towards expert 2 and 3 with weightages of 0.4 and 0.6 respectively. And token number 4 will be routed towards expert 1 and expert 3 with weightages of 0.5 and 0.5 respectively. So what I want to ask all of you here is that what does every column here in the expert selector weight matrix denote? And you can pause this video for a while to think about this. What does every column in the expert selector weight matrix denote? So the answer to this question is that every column essentially is for one particular expert. So the first column is for first expert, second column is for second expert, third column is for third expert. So if you look at the first column, it contains the probabilities with which tokens are routed towards expert number 1. So 0 is the probability of token 1 being routed to E1, 0.9 is the probability of token 2 routed to E1, 0 is the probability of token 3 routed to E1, and 0.5 is the probability of token 4 routed to E1. So now if I want to ask you the question that what is the total probability, or if you were to calculate a quantity which is called as expert importance, what will be the total expert importance for expert number 1 intuitively? So if you were to calculate the total expert importance for expert number 1, you will actually look at all of these probabilities and you will add them together. So if you add 0 plus 0.9 plus 0 plus 0.5, it will give you an answer of 1.4. So a summation of all of these values indicates how much importance is given to that particular expert when you consider all of the tokens. Similarly, what we are going to do here is that I am going to add the values. So I'm going to add the values of column number 1 and that leads me to a value of 1.4. That's the expert importance of expert number 1. If I look at second column, that is E2, and if I add all the entries of the second column, that will be 0.6 plus 0.4, that will be equal to 1. This will be the expert importance of E2. And now if I look at the column number 3 and I add all the entries of column number 3, that will be 0.4 plus 0.1 plus 0.6 plus 0.5. So that will be 1.6. This will be the expert importance of E3. So if you look at all of these importance values, you will see that expert number 3 carries the most importance and expert number 2 carries the least importance. Why is this the case? Because expert number 3 has of course more tokens routed to it with overall higher probabilities, and expert number 2 has only 2 tokens routed to it with overall lesser probabilities. That's why expert number 3 is more important than expert number 2 and also expert number 1. Okay, so this is the concept of expert importance, and this intuitive terminology of expert importance is exactly what we are going to utilize to calculate this auxiliary loss term, right? So ideally, what do I want? I want a balanced model, right? I want a balanced mixture of experts model. And what does having a balanced mixture of experts model mean? It means that all of the experts which I have, all of the experts such as E1, E2, E3, roughly all of these experts should have equal importance. It should not be the case that one of these experts has a huge amount of importance and another expert is completely neglected. If an expert is completely neglected, it means that no token will be routed to that expert. And we don't want such a situation. What will happen if no token is routed to an expert? That expert will sit completely idle and that expert will not learn anything. This leads to inefficient training and it also leads to inefficient inference. So ideally what I want is that these expert importance values, I want these values to be roughly similar for all of my experts. So what we are going to do is that we are going to penalize the mixture of experts model if the expert importance scores have a lot of variation. Because this would mean that some experts are more important than others. So essentially what we are going to do is that we are going to construct a loss. We are going to construct a loss term. That loss term will be very high if, so this loss term will be high if E1, E2 and E3 have a lot of variation, which means they are very different from each other. And that loss term will be low if E1, E2 and E3 are roughly similar to each other. So what I'm going to do is that I'm going to track a quantity which is called as the coefficient of variation. Coefficient of variation is a statistical concept and it's given by the simple formula. You just take the standard deviation and you divide by the mean. That gives you this quantity which is called as CV, or coefficient of variation. So what I'm going to do now is that I have three values, right? Expert importance of E1 is 1.4, expert importance of E2 is 1, and expert importance of E3 is equal to 1.6. I'm going to use these three values and I'm going to find the coefficient of importance of these three. How will you do this? You will first find the standard deviation of these three values. You will find the mean of these and you will divide the standard deviation by the mean. If this value is higher, it means the coefficient of variation is very high and the values are very different from each other. If this value is low, it means the coefficient of variation is low and the values are roughly similar to each other. And what you actually want is you want these values to be similar to each other so that the coefficient of variation is smaller. So we are going to define the auxiliary loss term, and that loss term is the scaling factor which is lambda into the coefficient of variation whole square. So my auxiliary loss I'm going to define as lambda, which is my scaling factor. It's a hyperparameter which we need to fix, multiplied with the coefficient of variation whole square. So higher the coefficient of variation, higher is going to be my auxiliary loss, and lower the coefficient of variation, lower is going to be my auxiliary loss. And so this auxiliary loss term is the term which I am going to add to the LLM training loss. So the LLM training loss is originally defined for the next token prediction, right? And this can be a categorical cross entropy loss, perplexity loss, etc. We are going to add the auxiliary loss term to this. And the amount of importance which needs to be given to the auxiliary loss is quantified by this hyperparameter which is lambda. And the CV here is of course coefficient of variation. So in my particular case, the coefficient of variation turns out to be 0.187. So we add the below terms to our LLM loss, and that is the scaling factor multiplied by with the coefficient of variation whole square. So what will this do? Addition of this loss term will actually ensure that the expert importance is uniformly distributed among different experts. If the expert importance is uniform across experts, the coefficient of variation will naturally be small, and that would mean that experts have relatively similar importance values. So this is the first concept which I wanted to teach you today, and that's the concept of auxiliary loss. Auxiliary loss was implemented in mixture of experts so that all the experts which I have relatively similar importance. And what is importance? Importance is essentially we look at the probability of the tokens, probability of one expert receiving the tokens, and then we add all those together. Okay, that's essentially what quantifies the expert importance. And I want these expert importance to be roughly similar to each other so that I have a balanced mixture of experts model. That's the first concept, which is the concept of auxiliary loss. The second concept which I want to teach all of you today is something which is called as load balancing. So it turns out that just having or just minimizing the auxiliary loss is not enough to make sure that the load is balanced across different experts. We need to do one more thing, and that is called as load balancing. So while the previously discussed token expert importance is useful, assigning equal importance to experts does not necessarily lead to uniform token routing. And this is a key concept. Assigning equal importance to tokens does not necessarily mean uniform token routing. And let me show this to you with a very simple example. Let's say we have those same 4 experts, or this example which I'm showing you right now is not necessarily a concrete example, but it helps illustrate the point. So when you take a look at the example, you'll see that the rows here do not sum up to 1, which they ideally should. But I'm just using this example to clarify this point that expert importance is very, very different than uniform token routing. So let's say if you take a look at these 2 experts, right? If you take a look at expert number 1 and expert number 2, and what I'm going to do is that first let me calculate the expert importance. What do we do to calculate expert importance? We look at the columns and we add the column entries together, right? So if you look at the first column right now and you add all the entries, this sums up to 1. So the expert importance for expert number 1 is 1. And if you look at the second column now, and if you add all the entries of the second column, these entries also sum up to 1. So the expert importance values of expert 1 and expert number 2 are both equal to 1. But take a look at the tokens which are routed to these experts, right? Expert number 1 has only one token which is routed to it, this token number 1. And for token number 2, token number 3 and token number 4 are not at all routed to expert number 1. Whereas expert number 2 has 4 tokens routed to it, token 1, token 2, token 3 and token number 4. This clearly illustrates the point that expert number 1 only has one token, but expert 2 is essentially hogging all the limelight. All the tokens are going to expert number 2, but the expert importance is same for both these tokens. So that clearly shows that just looking at the expert importance and making the expert importance same for different experts will not make sure that the tokens are routed uniformly to different experts. We need to have some other metric, and that metric is calculated through something which is called as the load balancing loss. So as I have mentioned over here, if you add up the probability scores for both the experts, both would sum up to 1. Hence, both the experts have equal importance, right? However, expert 1 has fewer tokens routed with higher confidence. Whereas expert number 2 has many more tokens routed to it, but with far lower confidence, right? Because the probability of tokens being routed here is 0.25. Uh, so what would be the issue if the tokens which are routed to experts are non-uniform? So if the tokens which are sent to each expert is non-uniform, it can lead to a high memory usage and a reduced mixture of experts' performance. And as a result, what we want to do is that we want to make sure the load of every expert is balanced. And what do we mean the load of every expert? It means the number of tokens which are received by every expert that needs to be balanced across the different experts. And that's why we implement something which is called as the load balancing. To do load balancing, there are essentially two things which we need to calculate. The first thing which we will calculate is the probability that the router will choose a given expert, and this is called as PI. So the first thing which we'll have to calculate is the probability that the router will select a given expert. And to do this calculation, it's pretty simple because we are just going to use the expert importance scores. So for these three experts, expert 1, expert number 2, and expert number 3, the expert importance values are 1.4, 1.0, and 1.6, correct? So the probability that the router will select every expert, or the probability that the router will select an expert for a given token is just going to be, for expert number 1, it's 1.4 divided by 4. For expert number 2, it's 1 divided by 4. And for expert number 3, it's 1.6 divided by 4. The reason we are dividing by 4 is because we want to have a probability, right? So the probability that my router is going to choose expert number 1 is 1.4 divided by 4, that's 0.35. The probability that the router is going to choose expert number 2 is 1 divided by 4, that's 0.25. And the probability that the router will choose expert number 3 is actually 1.6 divided by 4, which is 0.4. So if you add these three, it will sum up to 1. So it is important for all of you to intuitively know what PI means. So P1 actually denotes the probability that the router will choose expert 1. P2 denotes the probability that the router will choose expert 2. And P3 denotes the probability that the router is going to choose expert number 3. And these three probabilities add up to 1. Along with these probabilities, we are also going to find one more quantity, and that quantity is essentially the fraction of tokens which are dispatched to each expert. And this is the most important quantity which needs to be calculated along with the probability. Now let me illustrate why we calculate this quantity with a simple example. Let's say we take this same case, right? We have expert number 1 and expert number 2. And let's say we have 4 tokens, token 1, token 2, token 3, and token number 4. So let's say this is my scenario number 1. And I will also consider a scenario number 2. Expert 1, expert 2, token 1, token 2, token 3, and token 4. So let's say in scenario number 1, expert 1 hogs all the limelight. So I'm going to say token 1 goes to expert 1 with 1 and expert 2 with 0. Token 2 goes to expert 1 with probability 1 and expert 2 with 0. This is 1, 0 and this is 1, 0. And in the second case, token number 1 goes to expert 1 with probability 0.5. This is so, or let me say this is, let's say this is 0.6, 0.4. This is 0.4, 0.6. This is 0.6, 0.4. And this is also 0.4 and 0.6. Now what I'm going to do is I'm going to show you the calculation for the probability first and then the fraction of tokens which are routed to every expert, right? So in this case, so for E1 and E2, we are going to find the probabilities and the fractions, right? So this is PI and this is FI. This is PI and this is FI. So what is the probability that every tokens are routed to expert number 1? So we first find the expert importance, right? That is 4 and that is 0 in this case. And in this case, the expert importance is 0.1 plus 1, that is 2. And in this case, it is 2. So the probability that it will be routed to E1 is just 4 divided by 4, which is equal to 1. And the probability that it will be routed to E2 is 0 divided by 4. In this case, probability that the tokens will be routed to E1 is 2 divided by 4. and the probability that the tokens will be routed to E2 is 2 divided by 4. Correct? And now Fi is the fraction of tokens which are routed to every expert. So let's say I have 4 tokens, right? How many of them are routed to E1? All 4 of them. So the fraction of tokens is 4 by 4, and here it's 0 out of 4. And in this case, what's the fraction of tokens which are routed to E1? So token number 1 will be routed to E1 because E1 has a higher probability than E2, and token number 3 also will be routed to E1 because E1 has a higher probability than E2. So 2 tokens out of the 4 are routed to E1. So the fraction of tokens routed to E1 are 2 by 4, and the fraction of tokens which are routed to E2 are also 2 by 4. Okay. Now what we are going to do is that the load loss which we are going to do, it will be depending on a quantity which is called as Fi into Pi, which would mean that we are going to look at F1 into P1 and F2 into P2, and we are going to minimize this quantity. I'll tell you why we minimize this quantity, but first let's calculate this quantity for both of these, right? So this quantity is now F1 into P1 plus F2 into P2. So for the first case, what's F1 into P1? That's 1 into 1 plus 0 into 0. So this loss is going to be 1. And for the second case, what's F1 into P1? That's essentially 1 by 2 into 1 by 2, which is 1 by 4, plus 1 by 2 into 1 by 2, which is 1 by 4. So this loss is equal to half. So do you see something special over here? Essentially what you see over here is that the loss for case number 1 is higher than the loss for case number 2, which is what we wanted, right? Because case number 1 seems to be highly unbalanced. So expert 1 seems to be hogging all the limelight and expert 2 is not getting any token at all. Whereas case number 2 is much more balanced. Balanced in the sense that the expert importance is same across the experts, that's fine. But also the fraction of the tokens routed to the experts is also similar, right? Expert number 1 is getting 1 by 2. Expert number 2 is also getting 1 by 2. So I am getting a lower loss. So these are the two quantities which I consider in calculating this loss, which is also called as load balancing. And I will try to minimize this sigma Fi into Pi, which means I will get Fi into Pi for all my experts. I'll add them together and I'll try to reduce this quantity. What will happen if I try to reduce Fi into Pi? It will mean that, first of all, it will mean that I have a much more uniform distribution, because as you see, the more uniform the distribution you get, this product F1 P1 decreases. Whereas if one expert hogs the limelight, this product will go on increasing, which I don't want. So when I minimize this quantity, I will make sure that Fi is uniform and Pi is uniform across experts. And I want Fi to be uniform and I want Pi also to be uniform. If Pi is uniform, that makes sure that the experts have equal importance. But now I'm also saying that Fi will be uniform, and Fi is the fraction of tokens routed to that expert. So that satisfies the main thing which we started in this section, right? We saw that expert importance or auxiliary loss does not necessarily mean that the token routing is also uniform. So to make sure that the token routing is uniform, I include one more factor, which is Fi. And through this product minimization, I make sure that Fi is reduced and Pi also is reduced. So now I will show this a bit more formally. In our particular case, which we were seeing, we have already calculated Pi, right? For expert number 1, for P1 P1 is 0.35, P2 is 0.25, and P3 is 0.4. Now let's calculate the fraction of the tokens dispatched. So wherever it's 0.5, we will choose either of the experts, right? So in the case of first token, E2 is the expert which is selected. In the case of second token, it's E1. In the case of third token, it's E3. And in the case of fourth token, again, it's going to be E1. So fraction of tokens dispatched to expert 1 is 2 out of 4, which is half. Fraction of tokens dispatched to expert 2 is 1 out of 4. And fraction of tokens dispatched to expert 3 is again 1 out of 4. So as we can see, the F1 is 0.5, which is 2 by 4. F2 is 1 by 4, which is 0.25. And F3 is also 1 by 4, which is 0.25. And the load balancing loss is, as I mentioned, we have to do sigma fi into pi, and we have some scaling factor terms over here. We have a scaling factor, and we also multiply with the number of experts which we have. In this case, the number of experts is equal to 3. And the scaling factor is again a hyperparameter which we have to choose. So the load balancing loss is the scaling factor multiplied by the number of experts multiplied with sigma fi into pi, where fi is the fraction of tokens sent to expert I and pi is the fraction of the probability which is allocated to expert I, which also can be thought of as expert importance. So if you sum up fi into pi for these three tokens, for these three experts, I'm going to assume a lambda which is a scaling factor of 0.01, 3 which is the number of experts, and this is the sigma fi into pi. So this is f1 into p1 plus f2 into p2 plus f3 into p3, and that gives me a total load balancing loss of 0.0101. This is the loss which I try to minimize. Now you might be thinking, based on this formula, that how would minimizing this loss actually help us? So mathematically, this loss is minimized when the product fi into pi is minimized across all the experts, right? So the product will be minimal when both fi and pi are simultaneously low. And what would mean when fi and pi are simultaneously low? If fi and pi are simultaneously low, it just means that I am getting to a more uniform distribution. Whereas if one of fi and pi, if fi is very high, pi is very low, the distribution is not very uniform. And so this loss will be very high. So minimizing this loss is actually pushing me minimizing this loss is actually pushing me to reduce the overall imbalance between the assigned importance and the actual routing. So what this minimization of the loss term actually does is that it makes sure that my expert importance and my routing are aligned with each other, which means that whenever the expert importance is high, I'm also routing my tokens there. Whenever the expert importance is low, I'm routing less number of tokens over there. So I just want my fi and pi to be aligned with each other and also simultaneously lower together. When fi and pi is lower together, it means that my distribution is becoming more uniform. And when fi and pi are more aligned to each other, it means that experts with higher importance handle more tokens, experts with lower importance handle less tokens, and so there is no mismatch. Overall, this increases it increases the stability during training, and this also leads to a more efficient and balanced use of the mixture of experts architecture. Okay. So I hope you have understood the difference between these two terminologies. Auxiliary loss is something which is completely different than the load balancing. In auxiliary loss, we just look at the expert importance and we make sure the expert importance are equal among the different experts. And in the case of load balancing, of course, we take a look at the expert importance through PI, but we also multiply it with FI, which are the fraction of tokens which is routed to each expert. And this is the quantity which we try to minimize. This makes sure that the PI is uniform. So expert importance will be similar, but it also makes sure that tokens are routed uniformly across experts. Now, the introduction of this load balancing loss presents some other challenges which DeepSeek tried to solve, and they made one very major change in the load balancing loss, which we are going to see in one of the subsequent lectures. But to understand that lecture, it's very important for all of you to understand load balancing loss and auxiliary loss. The last concept which we are going to look at today is something which is called as the capacity factor. So let's start understanding about this now. So one more guardrail which we can implement to make sure that some expert does not hog all the limelight, or some expert does not get a huge number of tokens, like in this case which we saw, this expert was getting all the tokens, right? To avoid this, we can also implement something which is called as the capacity factor. So let's say we have not included capacity factor and something like this happens, right? The next day is, and if these tokens are all routed to one expert, that's not a good sign for us, because it means that expert number 2 and expert number 3 are not getting any of the tokens. So we introduce something called as the expert capacity or the capacity factor, and that's given by this formula. So expert capacity is tokens per batch divided by number of experts into the capacity factor. So expert capacity just means how many maximum number of tokens one particular expert can handle. If capacity factor is equal to 1, then it just means the number of tokens every expert can handle is the tokens per batch divided with the number of experts. So if I have if I have 1,000 tokens per batch, if I have 1,000 tokens per batch, and if my number of experts is equal to 4, it means that every expert can handle only 250 tokens. So expert capacity is the maximum number of tokens which every expert can handle, and increasing the capacity factor makes sure that every expert has more room to handle more number of tokens. And how do we calculate the tokens per batch? It of course depends on the context or the batch size. It depends on the sequence length, which is number of tokens which are passed into one context. And it depends on the top K. Why is there your top K? Because remember that every token will be routed to 2 experts or K experts, right? So the number of tokens are actually duplicated based on this top K factor which is there. If let's say I have top k equal to 2, if top k equal to 2 and I have E1, E2, E3 and E4, it means that my one token is now routed to 2 of these, right? My one token is routed to 2 of these. So every token will be routed to 2. So that's why we have to multiply the tokens per batch with the top k factor, right? So the expert capacity is tokens per batch divided by number of experts into capacity factor. So if capacity factor is equal to 1, then every expert gets an even split of tokens. If capacity factor is greater than 1, then every expert can handle more than its fair share. So which means that some experts can have more tokens while other experts, it's fine if there are less number of tokens. And that may happen in load balancing, right? If you do load balancing, it's not guaranteed that every expert will have same number of tokens. Some experts may have higher tokens. So if a capacity factor is huge, it might lead to a lot of imbalance, right? Which means one expert might hog the limelight. So generally what I've seen is capacity factor is in the range of 1.125 to 2, etc. The capacity factor never goes more than 2. Otherwise, one expert can hog all the limelight, and we try to solve this problem in today's lecture, right? That no one expert should have all the power. So it does not make sense to exceed the capacity factor by a huge amount. Whereas if capacity factor is less than 1, it means that we'll have to drop off some tokens. Because if we limit what every expert can handle to less than the total number of tokens, then we'll have to drop off some tokens. And that's also done sometimes when language models are trained. It's not preferred to drop off tokens. So for example, when DeepSeek V3 came out, the mixture of experts model which they have, they did not drop off any single token. So in this case, when expert capacity is not implemented, one expert can have 4 tokens like this, right? But if expert capacity is implemented, if that is equal to 2, if expert capacity is equal to 2, it means maximum number of tokens one expert can handle is equal to 2, right? So this actually means that expert number 1 cannot have 4 tokens. So if we implement expert capacity, expert number 1 will never be able to have 4 tokens. So we will never get some imbalance situation such as this. Expert capacity is actually implemented in many modern language models. I don't think DeepSeek version 3 implemented this, but they have novel architecture which we are going to come to later. But first, it was very important for all of us to understand step 1 to step 9 of how mixture of experts actually work. So in the previous lecture, I showed you until step number 7. And in today's lecture, I covered 3 things. I covered the auxiliary loss, then I covered something which is called as load balancing, and then after that I covered capacity factor. So there are 3 things which all of us have learned today: auxiliary loss, load balancing, and capacity factor. All of these mechanisms are in place to make sure that experts get a balanced load of tokens. So neither one expert should hog the limelight, and we should not have experts which are not doing anything. So we want to make sure that experts have relatively equal importance, right? And that's where auxiliary loss comes into picture. But at the same time, we also want to make sure that the fraction of tokens routed to experts is uniform. And that's where load balancing comes into the picture. And expert capacity just limits the maximum number of tokens one particular expert can handle through this capacity factor. Okay, so now once you learn all of this, ultimately it's important to understand the key advantages of mixture of experts. So if you have 32, 64, 128 experts, you get a speed up of 5 to 7 times. That's normal to see with mixture of experts. You get the training time speed up of a huge amount if you use mixture of experts versus if you do not use mixture of experts. So unlike dense models where all the parameters are used for every input, MOE only activates a subset of experts. And what this does is that it reduces the number of active parameters per forward pass, and that leads to lower operations per step, and it also leads to reduced memory footprint, allowing for larger models without too much increase in costs. So this one figure over here sums up the advantages of mixture of experts, right? It gives a huge amount of speed up as compared to if we do not use a mixture of experts model. In the previous lecture, step 1 to step 7, that covers the main mechanism of mixture of experts. But without understanding step number 8, step number 9, and the expert capacity, which was step number 10, it is impossible to understand the DeepSeek innovations which came. Because if you look at the DeepSeek innovations, the major innovations is something called auxiliary loss-free load balancing. And you would not be able to understand this innovation if you don't understand what load balancing is. So that's why we had to cover this lecture where I go through all of these concepts. And then we are also going to look at other DeepSeek innovations like shared experts, and the final innovation is fine-grained expert segmentation. We are going to look at all of these DeepSeek innovations in the coming lectures, so stay tuned. Make notes while I am explaining these lectures so that you understand these lectures in a much better manner. It is very hard to find videos which talk about these things in a lot of detail because these are not easy concepts such as auxiliary loss or load balancing. But I want to show you everything from scratch, and that's why I'm showing everything like this on a whiteboard. Thanks everyone. In the next lecture, we'll be embarking on a journey to understand the DeepSeek innovations in the mixture of experts modeling. So thanks a lot, and I look forward to seeing all of you in the next lecture.